All right, we have our introduction to the trigonometry functions, the trigonometric functions, and we have the derivative of sine and the derivative of cosine. And what I'm going to do is I'm just going to go through something you do not need to. In fact, I'll do this in this nice little Kansas City royal blue color. I'm going to go through the royal blue here. We're going to show the derivative of these. We're going to find out what the derivative has to be. What I'm going to do here in the blue is something I do not expect you to be able to reproduce. Once we get the final result, I will expect you to be able to use the final result. But I don't expect you to be able to go through this proof. The proof is in the text if you want to see it close, take a closer look at it. So let's take a look at what we have here. The derivative with respect to x of sine of x. By the definition, the derivative is the limit as delta x goes to 0 of sine of x plus delta x minus sine of x all over delta x. Sine of f of x plus delta x minus f of x over delta x. So the limit of the difference quotient. All right? Now the key to this is remembering a trigonometric identity that you learned and probably have long since forgotten way back in trigonometry. It says the sine of the sum, sine of a plus b. This is sine, cosine, cosine, sine. Sine of a plus b is sine of a, cosine b, plus cosine a, sine b. Sine, cosine, cosine, sine. And so by using that identity, the sine of the sum, this piece works out to be sine of the first, cosine of the second, plus, sine's the same sine, sine cosine, and then cosine sine. So that is the identity for this expression, minus sine of x. Again, this part in the blue, you do not need to be able to reproduce. I'm just showing you that I'm not pulling this rabbit out of a hat. There actually is a rational and logical reason as to why the derivative of sine is what I say it's going to be here in just a bit. The next piece to do here is I'm going to rearrange these terms. I'm going to take this term, which is this piece, put it together with this first bit, and then leave this all by itself. I'm going to rearrange, put this sign over here, and really what I'm going to do is just switch these two, the order of these last two terms. And while I'm at it, I'm going to split the numerator. So I'm going to put negative sign with this one. So I have sine of x, cosine of delta x, minus sine of x. Put those two together and split the numerator. So I put these two terms together, split the numerator, put this term by itself, split the numerator, and all of this is all within this great big limit. Now, the limit of the sum is the sum of the limits. But what we have here is something, well, if we just do substitution, we get 0 divided by 0. And so what we're going to do is factor out the sine. So this should be familiar by now because this is those special limits with sine and cosine. Factor out the sine, and what you leave is cosine of delta x minus 1. And all this is all over delta x. This is the first piece. But that is one of those two special limits we had. And remember, we had three forms. We had the 1 minus cosine, the same thing as cosine minus 1. So it didn't matter the sequence here. This limit is going to be 0. That was one of our special limits. And we have the same thing here. This is plus cosine of x times, we have sine of delta x over delta x. So we have this large expression here. But now we have it, because as delta x goes to 0, that's a special limit. That limit goes to 0. As delta x goes to 0, that's our special limit. That limit goes to 1. And so what we're left with here is sine of x times 0 plus cosine of x times 1, which is to say that's equal to cosine of x. And that is our final result. The derivative of sine is cosine. The derivative of sine is cosine. You don't need to be able to reproduce the blue, but you stinking better be able to reproduce this white. The derivative of sine is cosine. The derivative of sine is cosine. Using an exactly similar, the details would be different because the identity is different, but an exactly similar method, you can show that the derivative of cosine is not sine. The derivative of cosine is negative sine. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of sine is cosine. The derivative of cosine is negative sine. Those need to be bedrock without any question. Those need to be absolute, completely etched into your DNA. The derivative of sine is cosine. The derivative of cosine is negative sine. Now, what we can do with that is make a nice little observation. Again, this is not something you necessarily need to be able to reproduce, but to me this is a beautiful property. I'm going to very approximately draw this sine curve, and then very approximately again draw this cosine curve. There is a relationship between these two curves. The white is the sine, the blue is the cosine, and the relationship is here. Remember, derivative means slope of the tangent line. So the question is this: for the sine curve, for the white curve, at zero, this is the white curve at 0. The tangent line is here. The question is, what is the slope of the tangent line at 0? It turns out the slope of that tangent line is 1. At 0, the slope of the tangent line is 1. At 0, the slope of the tangent line is cosine of 0. That's what this value is, this 1. But at pi over 2, the slope of the tangent line is horizontal, within the limits of my terribly drawn picture. At pi over 2, the tangent line is horizontal. And so what is that slope? That slope is 0. What is the value of cosine at that point? The value of cosine is 0. That's what it means to cross the axis. The value of cosine is 0. At pi, the slope of the tangent line is -1. What is cosine at pi? Cosine at pi is -1. And so as the sine curve, as the slopes of these tangent lines change, the values of the slope of the tangent line, the slopes are given precisely by the function values of cosine. Now the derivative, or the effect is the same with cosine and sine, except you need to draw the negative sine curve. And if you do that, you can see that same relationship happening. So as these curves intertwine with each other, this property, this relationship is maintained. If you're not careful, this is almost a beautiful property. At 2 pi, the slope of the tangent line is 1, and sure enough, the function value of cosine is 1. At 5 pi over 2, the slope of the tangent line is 0, and sure enough, the function value of cosine is 0. Here, the slope of the tangent line is -1. The function value is -1. And so it's the same. Here it is. The slope of this tangent line is 0. The function value is 0. And so that relationship is maintained by these curves. And it's a fundamental property of the sine and cosine. It turns out that was contained within the definition of sine and cosine way back in basic trigonometry when you first learned the x, y, r definitions. This relationship of the slopes of the tangent lines to the graphs of the functions was inherently contained in the Pythagorean theorem. Remember, sine and cosine, all of basic trigonometry is just Pythagoras gone crazy. And so if you think about it, this relationship between the slopes and the function values of these curves is contained within that statement, ax, or a squared plus b squared equals c squared. And so Pythagoras is a rich, it contains much more information than at first blush you might think, and this is one example of that. Now, to be able to demonstrate that or be able to reproduce that is not the important point. That's not what you need to be able to do. What you need to be able to do is this. The derivative of sine is cosine. The derivative of cosine is negative sine.